In this video, we will cover XGBoost, one of those popular machine learning packages available for tackling supervised problems. We will discuss what XGBoost is, what makes it so special, and how this was achieved. Lastly, I will mention the various programming languages and frameworks that you can use to build your own XGBoost models. So we can begin by asking ourselves, what is XGBoost? So this just stands for extreme gradient boosting. So this is a type of boosting ensemble algorithm. And more specifically, it's a type of gradient boosting tree ensemble. Now, on my blog, I've written a couple of articles on gradient boosting. I have a link to both of those articles in the description below, so you can refer to those if you want to get into a little bit more details as to how gradient boosting actually works. But there are various different implementations of gradient boosting, and that's something to keep in mind. That scikit-learn has their own implementation of gradient boosting. There's also LightGBM is a different type of gradient boosting implementation. But for here, we're just going to be focusing in on XGBoost. Now, what makes it special is the fact that the algorithm and the implementation have been highly optimized for speed, for performance, and for handling large data sets. That's quite key. For data sets that are too large to fit into the memory of a single computer, that's something that XGBoost is designed to handle. So that's a key selling point for this framework. And fortunately, there are various different, there are different APIs in a few different programming languages and frameworks for you to build and deploy your own XGBoost models. And I will cover those in detail towards the end of the video. So now let's spend just a little bit of time going into gradient boosting. I'm not going to go into a whole lot of detail here. I'm just going to speak at a very high level. Again, I have included links to a couple of articles on gradient boosting that I've written in the description if you're interested in going into a lot more of the mathematical and programming details as to how gradient boosting actually works. So the key thing to keep in mind here is that it's an ensemble technique that operates sequentially. So in this scenario, we have a collection of very simple machine learning models, and we group all of these together. We have them work together to produce a net estimator that functions quite well. And boosting operates in a sequential fashion, and I'll illustrate that with an example shortly. And this is in contrast to bagging, where the ensemble functions in parallel. So each of the constituent models runs at the same time. Now, as I mentioned, each constituent model is going to be a fairly simple model, and typically we term this as a weak learner. Normally, the specific type of model we use here is a very simple decision tree, specifically a decision tree with only one split. That we can call it a decision stump. It's a very, very simple model, and that's typically what we use in XGBoost. The implementation is specifically just with trees in mind. So here we're just strictly speaking with the constituent models being trees. Now, the word gradient in gradient boosting comes from the actual details for how the updates are computed at each iteration in the algorithm. So what we end up doing is we compute the gradients of the optimization function, and we use those gradients in order to work out the updates that we use at each iteration. So that's essentially where the name comes from. And now if we want to just cover things in terms of just a very light example, let's imagine that we have a problem, we have a data set, and now we want to use a boosting ensemble to try and tackle it. So let's say that we have some data, and we're going to throw it in at this simple model. So what I've drawn here is a decision stump. So we've got a single root node and 2 leaf nodes. That's it. This model will try to make predictions on the data that we throw at it, and now it will get some of those predictions right and a whole lot of them wrong. For such a simple model, that is what we would expect. But what is going to happen here is that we're actually going to take into account, or we're going to record where this model got things right and where the model got things wrong. And we're going to use that information to weight more heavily the samples where the model got things wrong. And then we're going to pass that information along to a second model. So now we're going from the first model to the second model. And now the second model gets to focus in on the cases where the first model made mistakes. So now the second model has a bit of a leg up on things because it doesn't have to try and tackle the problem in its entirety. It's going to zero in on just those cases that the first model got wrong. Now the second model gets its own attempt at making the predictions. Now it's going to get some of them right, some of them wrong, and we repeat the process. So now we record where the second model got things wrong. We weight those samples more heavily, and we pass that information along to yet another decision stump. And now this third decision stump gets to focus in on just those samples where the first 2 models got things wrong. So we can continue doing this. We can continue at each iteration. We just add on another decision stump and keep attacking the problem that we have. And in this way, we can build a very powerful estimator for doing supervised learning. So what's different with XGBoost? So the first thing that we should point out here is that XGBoost models tend to have excellent performance when working with supervised problems. And so this is a general point to make for all gradient boosting models. And I can speak from my own personal experience in industry that, if we're building a solution for a supervised use case, typically we will build that solution around XGBoost. So it definitely is a package that is used in industry to solve real-world problems. So it's definitely effective in that sense. Now it's also very quick. It operates very fast when working with these real data sets. So one of the points that differentiates XGBoost specifically from other implementations of gradient boosting is the fact that it's been highly optimized for computational speed. Now, related to that, there's also the strong emphasis in the way that the algorithm has been designed and also the way it's been implemented on supporting distributed and parallel computation. And that's key for the next point, which is that we are able to support very large data sets. And that's key. So with XGBoost, we can translate the most extensive data sets, and we can get business insights out of those data. We can generate a predictive model based on those data, and we can do that in a reasonable amount of time, right? Because the computation speed is good, and also because the model is designed to support distributed and parallel computation. So it also makes the most efficient use of the computational resources that we have available. And those are really the key selling points for why XGBoost has become so popular. And I like this quote, and yeah, this comes from the paper, the 2006 paper by Tianqi Chen and Carlos Gestrin that describes XGBoost. So the quote reads, "Take the challenges hosted by the machine learning competition site Kaggle, for example. Among the 29 challenge-winning solutions published at Kaggle's blog during 2015, 17 solutions used XGBoost." So that just highlights the preponderance of using XGBoost to solve a competition like Kaggle. And in the data science community, it's kind of common knowledge now that if you want to try and solve a Kaggle competition, you throw XGBoost at it, and most likely you'll have something that's halfway decent at the very least. So how does XGBoost achieve all these points that we just talked about? So one of the main elements is the emphasis on building a scalable gradient boosting algorithm. Now let's touch on how exactly that's done. So one of the main things is that an approximation to the greedy learning algorithm is implemented in XGBoost. Normally, decision trees, and by extension, gradient boosted trees, use a greedy learning algorithm in order to learn the model parameters from the training data. This involves iterating over all the different input features and all the unique values for each of those features in order to work out an optimal configuration for the split point at any node in our tree. The problem with this approach is that it involves loading in all the data into memory. And so that could pose problems if our data set is quite large. And so instead of that, we use this approximation that gets around that issue. So this approximation involves proposing candidate split points using a novel distributed weighted quantile sketch algorithm. And so this is just an algorithm that is used to propose out potential split points, makes a fairly good guess at those split points, instead of having to do this very mechanical, greedy procedure that's normally done with decision trees. Now, continuous features are then mapped into buckets that are defined by these proposed split points. And then the algorithm identifies the best option out of all of these proposals. In addition, the algorithm is also sparsity aware, meaning it is able to handle data with missing values, zero entries, and engineering artifacts. You can think of one-hot encoding as an example of a feature engineering artifact. Now this is done by adding a default direction to each node in the tree for over the entire ensemble. So here's an illustration of this. We have a very small data set shown in the table with a couple of missing values and then the associated tree that goes along with that data. And the default directions at each of the two nodes is given in red. Now, these default directions are not just picked out of the hat at random. Instead, optimal default directions are are determined when training the XGBoost model, and they're learned from the data. Now, as another attribute of this, the computation complexity is linear to the number of non-missing entries in the input. So not only are we enhancing the performance of the algorithm, but also the computation complexity is also quite good. Now, continuing on with the emphasis on building a scalable solution, the next element focuses more on how we implement the solution. So the data is stored in in-memory units called blocks in order to reduce the time of sorting. So normally with a tree-based algorithm, you have to sort the rows in your data set in order to compute the split points. That's something that's done internally, and that can take some time. So instead of doing that, or to minimize the time doing that, we're going to split the data up in memory into these partitions. Now, these blocks correspond to a subset of rows in our data and can be distributed across machines if we are using a cluster. On a single machine, they can be stored on disk in the out-of-core setting. Collecting statistics for each column can be parallelized, giving us a parallel algorithm for split finding. To reduce overhead due to read-write dependencies, we make this procedure cache-aware. Now, what does that mean? A cache-aware algorithm is explicitly coded to take advantage of a processor's caching behavior and is designed to minimize the movement of memory in and out of the processor's on-chip memory cache. So the last point that I want to touch on for this section is, again, something related to the algorithm, the way that's implemented, and that is that regularization is built into the objective function in XGBoost. So we can see that here. This is the optimization function that is used in the implementation, and we see that it consists of two terms. So the first term is just our regular loss function, and that increments over I, and I is the number of samples in our training data. And then the second term with the summation over K, K is the number of elements in our ensemble. So it's the number of decision stumps, the number of constituent models in the boosting ensemble. And omega is a regularization term. And essentially what this does is it penalizes overly complex models. And what this helps us do, what this helps XGBoost do, is to prevent itself from overfitting on the training data. Overfitting itself is something that is a common problem for decision trees and for boosting ensembles in general. So this also helps to enhance the performance of the XGBoost model. So having said all of this, perhaps now I've convinced you that XGBoost is a good model to try out for your supervised problem. How can you go about doing that? Well, there are various programming languages that have an API in XGBoost. So we have Python, R, Java, Virtual Machine, Ruby, Swift, Julia, and C and C++. There are APIs in each of these languages where you can build your own XGBoost model. Now, on top of this, one key thing to keep in mind is that XGBoost also provides GPU support. So if you need some extra computational muscle to solve your problem, you can do that with XGBoost. And as well, we of course have distributed computing support. And we can use one of these three frameworks, so Spark or PySpark, Dask, and Ray all provide an API for XGBoost. So you can take your pick to see which technologies best suit your project. So this concludes the video. I hope you got some value out of it. If you have, please like, share the video, and certainly subscribe to the channel. I have in the description below a link to my blog where I have a couple articles where I do a deep dive on gradient boosting, the algorithm, and how to implement it from scratch as well. So you can feel free to check that out. I also have included there the homepage of XGBoost, so you can, if you want to take a closer look at this package, you can do so there. And I also have a link to the 2016 paper that describes XGBoost by its authors, so you can also check that out as well. So yeah, I hope you have a great day and see you in the next video.